Hi, George Romanic here. Welcome to Fundamentals of Weather and Climate playlist. In a previous video we discussed the concept of relative humidity and how it is the most used variable to describe the water vapor content in the atmosphere to the general public. However, this quantity depends on temperature and therefore it can be misunderstood. Fortunately, you're watching this video so you will know how to properly interpret this variable. Let's see what is the issue with relative humidity. Relative humidity is the ratio of the partial pressure of water vapor divided by the saturation pressure of water vapor, which depends on temperature times 100, and we multiply by 100 to give results in percentages. And here is the issue. Saturation vapor pressure depends on temperature. We know, let me plot here, from my video on the saturation vapor pressure, that if we have ES here and temperature here, that the relationship is a power law described through Clausius-Clapeyron equation that I described. And you can see that as we increase temperature, the saturation vapor pressure also increases, and in a nonlinear fashion. So that means if we keep E constant, but we decide to increase temperature, that will immediately from this relationship result in ES being increased. But from this equation you can see if ES increases, that relative humidity will decrease. So relative humidity will decrease despite the fact that we did not add or remove any moisture from the air. And that can be problematic when we want to understand how much moisture is in the air. Because think about this graph. If here we have time in a 24-hour period, so we start here as 00, here is 06 local time, here is noon 12, here is 1800, and here is 2400 hours. And here I plot temperature. In a 24-hour period, you know from my videos on temperature that temperature profile might look like this. If we start from some value, then the minimum temperature is achieved around sunrise, and then temperature rises, maximum about 3-4 p.m. local time, and then temperature decreases to maybe reach similar value as the midnight before. So this is how temperature changes throughout the day. Now, let us assume that we keep E constant. Namely, during this 24-hour period, there was no addition or removal of moisture from the atmosphere. If I now put a secondary y-axis over here, let's put secondary y-axis over here, and this secondary y-axis will measure relative humidity. How is relative humidity going to change? Well, if I start from some value, I don't know, let's say I start from value here, then as temperature is decreasing, relative humidity will increase. As temperature is increasing, relative humidity will decrease, and then maybe it will reach similar value as the night before. So in other words, we did not add and we did not remove vapor from the air, but the quantity that we use to describe motion is varying throughout this 24-hour period. And that is happening because temperature is varying. So from that point of view, there can be misconception of interpreting relative humidity. What relative humidity is good about is to tell us how far away from saturation is our atmosphere. And that's perfect. If relative humidity is 70%, we are 70% saturated. In other words, we are not saturated, we need 30% more of water vapor to get saturation. But what relative humidity is not good about, and it cannot tell us anything about it, is what is the actual amount of water vapor. It tells us what is the amount of water vapor with respect to saturation. But in absolute values, what is the actual amount, we don't know anything about. And I can demonstrate that even further, because you will see, if I erase this, that relative humidity of, let's say, 60% in the tropics and polar regions means something completely different in terms of the actual amount of water vapor. So let us assume, and let me use black again, let us assume that relative humidity is 60%. Now, we will have option A, we are in tropics, close to equator. Let us here assume that tropics are warm, so temperature is, let's say, 30 degrees Celsius. Now, at 30 degrees Celsius, it happened that I know that saturation vapor pressure at 30 degrees Celsius is about 42 hectopascals, or 42 millibars. So that means, therefore, that I can calculate this E by rearranging this equation. Namely, E will be relative humidity times ES as a function of temperature divided by 100. That comes from this equation. Well, that is equal further. Relative humidity, I just told you, is 60% times ES of T is 42 hectopascals divided by 100. And I don't know the value, so let me take a calculator to calculate this. So if I go to calculator and I say 60 times 42 divided by 100, I get 25.2 hectopascals. This is the actual amount of water vapor in the air in the tropics. Now, case B, let us say we are in polar region. In polar region, temperature might be 0, okay? 0 degrees Celsius. Now, everybody should know from my video on the saturation vapor pressure that saturation vapor pressure at 0 degrees Celsius is, of course, 6.1 hectopascals. Now, if we use this equation in the case of the polar regions, then relative humidity is the same, 60, times saturation vapor pressure is 6.1 hectopascals divided by 100%. And if I multiply these numbers, what am I going to get here? I get 60 times 6.1 divided by 100, and that is equal 3.66, 3.7 hectopascals. Here 25.2 hectopascals, here 3.7. If I divide these numbers, 25.2 divided by 3.7, I will get that the ratio is 6.8, around 7. That means that despite the fact that relative humidity in the tropics and polar regions is the same, because temperature in tropics is much higher than in polar regions, the tropics has 7 times more vapor, water vapor in the air than the polar regions. But relative humidities are the same, okay? So the amount of water vapor in the air is not described by relative humidity. That's why the term relative humidity. Humidity measured relative to saturation point. In both cases, relative humidity is 60%. We are 60% to reach saturation. But because in polar regions saturation would be reached much faster than in tropics, because temperatures are lower, those relative humidities are the same. So now you listen video lecture on relative humidity and you saw a lecture on the issues related to relative humidity. Issues if you don't know how to interpret it. Fortunately, you do now because you watched this video. This is another reason why in atmospheric sciences, in research, people tend to use mixing ratio, specific humidity, difference between temperature and dew point temperature as another measure of water vapor content, because these quantities can sometimes give us better picture about water vapor content, particularly mixing ratio and specific humidity. Please check those videos if you are not familiar with those concepts. Please make sure to like and subscribe, share this video, comment, and until next lecture, goodbye.